Hi, Justin.
Hi, Julian. Thanks for having me.
Thanks a lot. It's been a while. I tried to get you on the podcast because I know all what you do, and I've seen you lots of time in a congress and conference, and it was really interesting about what you're doing on ACL and the brain. And I think it's improving a lot how practice in rehab. So I'm really happy, and I'm lucky to get you on the podcast today.
It's my pleasure, Julian.
Yeah, thank you very much. And to start, can you give us your definition about the performance?
Of performance?
Yeah.
So my background is mostly as an athletic trainer, which is sort of like a physiotherapist in Europe. We only specialize in sports injuries. So my first level definition of performance is simply the absence of disease, pathology, or injury, since I usually come at things from a medical perspective. And then layering on top of that is an optimization framework for performance. So based on your genetic potential and the current structure of your body and your current capabilities, how do I arrange the session or the training session or the game situation so you can have the best outcome possible? So performance is always tough because it's always variable based on the situation. So your football player's performance is going to be their view of performance is scoring the goal, winning the game. Your patients could just be contracting a muscle. So performance is highly variable, but that's how I tend to think of it in these two different aspects.
Nice. And can you tell us more about your background? You said you started as you said you started as an assistant athletic trainer. And can you tell us the difference with a physio?
Yeah. Well, it's a good question because it's a bit of a weird, there's not very many physiotherapists or athletic trainers that go in to study neuroscience. It's pretty rare. And so I can tell you a little bit about this, how I ended up doing this. So in the United States, we have physical therapy and we have athletic training. It's sort of just an accident of history that they're not one profession like in Europe, where it's more physiotherapy. And a lot of that is because physical therapy came out of the medical model, working at hospital clinics. And athletic training started out as like the equipment managers or the people working with the sports teams. But what they found was there was such a high rate of injuries in sports, as we're all probably aware, but there was no one providing medical coverage. So in the beginning, it was just these sort of managers or equipment people or other support staff that were part of the teams. This is back 60, 70 years ago.
Okay.
And they started to take on some of the medical duties, trying to keep the players playing. And so the big difference between the two is athletic training came out of a perspective that they want to do everything they can medically to keep someone performing, even if they are injured. Whereas physical therapy in the United States came out of you are injured, you're no longer playing sports, and now you're going to get therapy. My understanding is in Europe, and you might correct me, Julian, is sports physio is sort of a combination of the two. Okay.
Yeah.
And so my background, I was really interested in sports and sports medicine. And so I went into the athletic training path, which is sort of a mesh of the sports physio. They don't do a lot of the strength and conditioning. I know in Europe, the athletic trainer tends to be more performance-based. In the United States, it's more medical-based. But there's still a bit of a hybrid sort of role. So I was treating patients, and I'll never forget, I had a football or a soccer player. I know you prefer football term. And I was working with a football team, and he tore his ACL when I was a clinician. And I go out onto the field and I do the exam, and he did the Lockman test. I was like, oh, he's torn his ACL. I take him to see the orthopedic surgeon, and the surgeon does the surgery, he does the ACL reconstruction. And I have this moment where I'm like, well, I went to school for this. I know what I'm going to do. I did all his therapy for 9 months, and he was stronger on his injured side than his healthy side. And I was like, this. I did great therapy. I returned him to sport. He goes to plant and he blows out the graft. And as a clinician, as a I just couldn't handle that sort of psychologically or emotionally. Like this idea that my rehabilitation has this high rate of failure, that I could do everything right and the person could have a bad outcome, I just found to be unacceptable. And so I think anyone who treats patients like yourself or your audience that are, I know they're mostly physios, you're going to have this eventually where you do everything you were supposed to do and the person doesn't get better or they re-injure. And so after a couple years, I thought, well, maybe the answer has to be in science. Like there's no other path for us to figure out why he got injured again. What did I not do in my therapy when I thought I did everything right? And so that's when I looked at do a PhD, which is a scientific degree. And I started out in biomechanics, which is the study of how people move. And it uses like markers on the skin, and you quantify kinematics, and you put force plates in the ground, and we get an idea for how people are moving. And that technology is great. It tells us how people are changing their movement and what movements lead to injury and these sorts of things. But it doesn't tell us anything about how the nervous system is generating that movement. It just tells you like the outcome. And so I switched to neuroscience after a year of studying biomechanics because I didn't think the answer to my question was going to be in biomechanics, which is what orthopedics usually does. And then that was about 13, 14 years ago. And so we've been studying the nervous system ever since after these orthopedic injuries. And I think it almost has to be the missing link in the patient that looks great on every other measure, but they get hurt anyway, or they don't do as well, or they don't return to that optimum performance. I don't know if we found the 100% right answer yet, but I think we're in the vicinity of getting close to figuring out what exactly is missing.
Yeah. Agree. And I think we are getting closer and closer. And like the brain part is just huge. And can you explain us? We talk about ACL injury, and we know that it comes from a sensorimotor control error. And why does it happen? Since when you started, when it happened to your patient, and now what do we know, and what do we don't know?
No, it's a good way to frame it. It's a good question. And I actually appreciate you asking, like, what do we not know? Because I feel like, and when you do really hard scientific training, you get very comfortable with being wrong or having your hypothesis not be 100% accurate or this unknown factor. Because every time you publish a paper, the idea is that, well, this is some new piece of knowledge that we didn't know before. So the ACL injury, thinking about it as a failure of the neural control system, is really a pretty new idea. So some people had speculated on this. There's a great paper, I think in 2005 or 2006. It's by Scott McLean. He was an engineer. It's in the Journal of Athletic Training, and it's called, it's like the ACL Enigma, something to that effect. I can send it to you after the call, Julian, if you want to include it in the podcast notes.
Yeah, thank you.
But it's only like 2 pages, and it's maybe it was a little later, 2008, but I'll send it to you. And so basically he's talking about like ACL injury is this non-contact injury, is this bizarre enigma because we study it, we do it in an intervention, and someone could land perfectly from an ACL injury prevention program, but they still go on and have a non-contact injury. You look at like the FIFA 11 Plus, which is probably the best, most researched injury prevention program. If you look at their data, almost every single paper, someone gets a non-contact injury in the intervention group. So even if we do our best therapy to prevent it, there's still something we're missing. And Scott goes into this paper, again, it's very short, but he makes this pretty clear argument that there's something else besides just the biomechanics going on. We don't know what it is. So that was before I started my PhD, before we started this path. And it was very forward looking. And then there's Francisco Della Villa and his father, Stefano Della Villa. They've been publishing these papers, and they've had these ideas for a very long time that there's something in the nervous system that's predisposing them to injury, but they never really had the tools or the science or the ability to really detect it. And recently he's published these papers where he's looking at these injury events, and he asked this question. This is Francesco. He asked these questions. Well, what is going on around the player at the time of injury? What he often finds is that there's some sort of cognitive demand or a cognitive error, which means they fail to make the right decision, or they're highly distracted right before they make this. They place their foot in a position that's not optimal. And so this is what I would call like circumstantial or behavioral evidence that says there's something bizarre going on here. And then if we look into neuroscience, well, maybe neuroscience could tell us, do we have enough data now to have a hypothesis for this? And what's really amazing with this idea is that we've only been able to measure the human brain since about the late 80s. We had the breakthroughs in fMRI where I could measure your brain while you were awake doing activities. Up until then, we had very low, poor resolution technologies. You had EEG, but really it was the breakthroughs in the 80s with fMRI that allowed us to scan the brain and look at the brain activation pattern during tasks. And even that technology is not very robust, so it's still a grainy picture. It's not a full like iPhone picture, like very crisp and clear, but it's the best technology we have right now. But that propelled this breakthrough that I can look at the brain while you're trying to control your legs. And with this understanding of what the brain is doing during motor control, there's this exceptional theory that really frames what the cortex does. And there was a lot of debate through the 70s and 80s on what does the cortex do? And what we now know, it seems to be that the cortex across your whole brain, which is everywhere, it tries to engage in what's called essentially prediction. And so your visual cortex is trying to predict what you're going to see. Your motor cortex predicts where you're going to be. Your sensory cortex predicts what you're going to feel. And every time those predictions are right, you have just a little bit of neural activity that confirms the prediction, and you go about your life. This is where neural efficiency comes from, which we may talk about in regards to after the injury, what happens. And so to have a neural efficient response, meaning minimal neural activity, which means you have an optimal performance usually. These two are pretty well tied. You want to be more neurologically efficient, have better performance. Rests a lot on the accuracy of your sensory predictions. And so when you look at Francisco Della Vila's injury videos in his papers, it looks like they're predicting their foot to be just a little bit more medial, but it's a little more lateral. And so they fail to contract their glutes and with enough time, and the knee goes into valgus and it ruptures. And so we had some pretty interesting data on some people before the ACL injury event. And there's one pathway in the brain that allows you to correct for slight errors in your sensory prediction. So if you ever have the experience, Julian, where maybe you're walking down the street and you hit a pebble or something, or you hit a bump or the curb, and you stumble a little bit, but you don't face plant, you immediately take another step and save yourself. You were able to do that. You made a slight prediction error, but the sensory cortex had a rapid communication with the cerebellum, and it created an immediate motor correction very fast before you were aware. If you think about it, if you had to look down and realize you were falling, we would never survive as a species. It'd be terrible. So we looked at this pathway and a large cohort of people before the season. And this was a data set that we were looking for. It was a concussion. So they had baseline data. They do the football season. Yeah. They did American football, and we had European, we had soccer. We looked at people who had ACL injuries. The people who went on to ACL injury, they had lower connectivity, or the ability to communicate between the sensory cortex and the cerebellum. And so that predisposed them, we think, to have a slower correction to the sensory prediction error, exposing them to a higher probability of ACL injury. And so this is where the theory begins with our best understanding what the cortex does, predicting the world, that allows you to have neural efficiency, to have low neural activity, to engage in the world. And then we think the injury event happens when you make this slight prediction error on where you think you are in space relative to the ground. And you then you fail to make a cerebellar correction. So you have to have the prediction slightly error first, which we make these constantly. If you reach for something and you're a little bit off, or you're at dinner and you reach for your wine and you tip it over, this happens to everyone eventually, because your neurons are just electrical signals in a soup of chemicals trying to guess where everything is in the world. It's not 100% accurate. It's a biological system. So you have this slight error, but we have the cerebellar connection to help you correct for it. And if that's not connected, or it's a little bit off, like in those that went on to non-contact injuries, then you've lost the ability to correct for that slight fuzziness in the prediction, predisposing you to make coordination error. I know that was a long explanation, Julian. If you have questions, please clarify.
It's huge, and so it could come from because you're too slow between your cerebellum and the other part of your brain. And is it like from scratch? So you are born and it's like this, or it's just because you get concussed, or it's just because because like fastness, you can grow up and being fast and grew up and being not too fast, maybe more endurance. And is it the same for your brain, or?
Yeah, that's a great question. So it's both. So you can train sensory cerebellar connectivity. It's a little hard, and I'll tell you how to do that in just a second. But there's also, you start out with a certain base coordination ability. So a lot of it has to do with the sensitivity of your proprioceptors. So there's also a genetic predisposition to proprioception, which is knowledge of where your joints are in space without seeing them. So I can touch my fingertips together with my eyes closed, because we all have proprioception. And so that is genetically regulated on some level. The volume of mechanoreceptors in your tissue, genetically regulated. You can't really deal with this. So it's the same, like you were saying, a bodybuilder, very strong guy, maybe he has more muscle fibers than someone who doesn't have, right? And you can't really do a lot about that. You can make the ones you have larger, but if someone has a lot more, it's difficult to deal with. Fiber type of muscles is also genetically regulated. Mechanoreceptors and the ligaments in your tissue also genetically regulated. So that baseline will have a genetic predisposition. Now, you can train sensory prediction and this correction ability. To do that, you have to basically induce prediction errors and force a rapid correction as possible. And so the problem with training this in humans is we'll tend to use vision and we'll tend to use cognition, which is like our direct focus on a task, because it's very powerful. And so the problem with a lot of our therapy is that you'll allow them to think about the movement that they're doing. So you're trying to do a quad set after an ACL injury, you're staring at your quad, you're thinking about the muscle. You're training them to do a squat, you're telling them all the techniques, you're telling them what to do, they're focused on the movement. Most of physical therapy, athletic training, or rehabilitation is allowing the patient to dedicate all their attention to the task. This does not train sensory cerebellar connectivity at all. This trains what we call frontal parietal connectivity, which is the frontal cortex with the sensory cortex, which isn't what you use that when you're thinking about what you want to do. So if you picture the footballer, he's using frontal parietal connectivity to think about where the other players are, where he is, the game strategy, what the coach is telling him, that sort of thing. You're using sensory cerebellar connectivity to just control your body naturally. So he's running down the pitch. He's not thinking about where his knee is, where his ankle is. He's relying on the sensory cerebellar cortex, which is, we would call implicit control. And he's doing it automatically. And so in physical therapy, you have to find a way to not let them use their attention and their vision. And then you can push them to use the sensory cerebellar connectivity. There are a lot of ways to do it. One is you can just occupy visual attention and their cognition and force them to use the other system. Strobe glasses is one. You can use virtual reality. I know you have some other questions. We can talk about those. You can also just do dual tasks. So you're essentially saying, I'm going to occupy your attention, and maybe that'll force you to use your sensory cerebellum, use your implicit control. Other options are to try to design your therapy where it's more reactive and they have to generate as fast a response as possible. So instead of doing 3 sets of 10 on a knee extension, maybe you're having them hold a hamstring contraction, and then you're like you give them a signal, they have to suddenly explode and do an exercise. So you're trying to force them to generate a motor action as fast as possible to a cue, preferably make it proprioceptive cue. So they're like, maybe they're kicking into you, like you're holding their shank, and then suddenly you release it and they have to like pull it back really fast. And so that way it's proprioceptively regulated and they're trying to generate some sort of correction to an unexpected situation neurologically. So you kind of have these two paths. I can occupy the system they're compensating with, or I can try to train sensory corrections in clever ways like the force release, or there's some other methods I think we'll get to during our discussion. But those are good questions. So it's trainable, but it's also partially genetically regulated.
So it's both, yeah. Thank you very much. And I wrote effectiveness of brain work after other injuries like ankle sprain or muscle strain. Is it the same in your brain? That is your brain like with neuroplasticity and everything? Is it moving the same for a muscle injury than for an ACL injury?
Yeah, it's a good question. So most of the data, we focus on ACL injury scientifically for a few reasons. One of the ACL, it's a kind of a homogeneous injury. So people tend to have a complete rupture of the ACL. There are partial tears, certainly, but most commonly it's a total rupture. And the injury is pretty standard across most people, and the surgery is very standard, the rehab is very standard. So it's easy to study scientifically. Ankle sprain's a little harder. You could tear the anterior tibiofibular, the calcaneal, the posterior. You could have deltoid, you could have syndesmotic, whole mess of different injuries, all different implications. There are a few groups that study ankle sprains, though, and they show a pretty similar neuroplastic effect to the ankle. In some ways, the ankle it's a little more complicated, but it has a larger cortical representation. Like your foot and your ankle have a lot more neural drive to them than your knee. Your knee is very, very simple, very spinal regulated. It certainly has its own representation in the brain, but as you might imagine, the ankle and the feet have a lot more proprioceptors, have a lot more degrees of freedom, especially in like soccer, football. They're going to have a lot more demand. So the ankle might induce a larger effect depending on the degree of injury. The muscle strains are less studied. They're a little tougher. There is a group that is doing hamstring strain, and they had some interesting data presented recently. I don't know if they've published it yet, where it does look like the hamstring strain, especially repeat hamstring strains, induces a similar neuroplastic effect. And there's his name's actually Julian as well. There's a guy in Brazil working on this as well. And he's seeing some similar data. So it looks like this injury effect where you have this shift towards visual and frontal and sort of sensory integration region activity, you see a similar. So I would apply the same principles to all of my musculoskeletal therapy.
Yeah. So it could get like an injury signature, an injury brain signature after any other injury. So,
correct.
Yeah. So for our rehab, we should finish with the same kind of, not only finish, we should work every time on the brain part, not only on the muscular system and not only on the balance, but we should also work like with cognitive, with dual task, with everything for any injuries.
I think so. I mean, I don't think there's a low risk doing it as long as you're doing your fundamental therapy, but layering this on top is probably a good idea for anything. I agree.
Good, thank you. And how the brain perceives limb position and movement after an injury? What kind of change? Is it because you get an injury, so your brain doesn't want to move anymore, so you don't know how to feel your knee because there is it's swollen and you have lots of fluid in it, so you don't know what it is like extension and 90 degrees of flexion. Is it this?
That's a good question. So your first or initial questions were more about the initial injury event and the sensory prediction error. And so what we see after the injury, this sensory prediction ability is worse. It's dampened. So you have two sort of constructs to generate your prediction and refine it. So one is your experiences. So how accurate was your last movement to inform your next movement? This is your classic motor learning. We find that motor learning is largely refinements to your predictions. You get better at the movement because you're better at predicting how it's going to go. Makes it neurologically much less demanding. Learning a new skill requires a lot of brain activity. Doing the same skill you've done 1,000 times requires very little brain activity. And so this is where you get efficiency and improved performance. And so after an injury, you have this disruption in the feedback coming in, which is what you use to update your next prediction. So the very data that allows you to refine your predictions in the brain is disrupted because the proprioceptors in the ACL are gone. The brain has been used to getting that information for your whole life. You've always had an ACL. It's always been there. And we find regardless of reconstruction or if you remain deficient, there is not really a high quality reinnervation of the ligament. Most of the data that says you do get reinnervation is mostly of the pain and the C fibers. You do not get the type 1A afferents, which give you sense of position. So that's essentially lost. And so what the brain does, it compounds the sensory prediction problem that led to the original injury. So normally, as you mentioned, I could rely on, in part, the strain on the ACL, the tension, to let me know where my knee was in space, because as I go towards extension, it becomes a little more taut, and I know I need to protect it, have a hamstring contraction. As my knee rotates into valgus, I get explodes, and I'll contract my glutes to help me not go down, contract my hamstrings as well to protect it. So what you're really depending on there are 10 to 30 milliseconds for the reflex. So the ACL starts to get under tension, you have the reflex contraction, you save yourself. You don't blow out the ligament again. After the injury, the predictions aren't as refined because you have that disrupted information. So you're going to be a little bit slower, but something else starts to happen. And this is what we call cross-modal plasticity. So cross-modal, it sounds like a complicated term, but modal or mode just means a mode of sensory perception. So I have proprioception is a mode, vision is a mode, vestibular feedback on where I am in space. These are all the sensory inputs you have. And you have areas in your brain, some are unimodal, which means they only do vision, they only do proprioception, they only do vestibular, they only do auditory, etc. You have some multimodal, which means they will activate for 2 or 3 or all of the sensations. And so like you think like sensory cortex is only proprioception. Visual cortex of E1 through 7, only vision. Now between your sensory cortex and your visual cortex, so like from here to here, you have this whole rest of your parietal cortex and a bit of your occipital cortex. So it's about a third to a quarter of your whole brain right here. It is full of these regions of multimodal that integrate multiple senses and cross-modal regions. What's unique about a cross-modal region is it tries to detect, do I have a discrepancy in one of my senses that I can confirm with another sense. So if you have this little bit of error in proprioception, which we have in case of musculoskeletal injury, for any injury, muscle strains, you lose muscle spindles, you lose GTOs, ankle sprain, ACL, whatever. So I have this slight disruption in my sensory cortex that it expects to get information. Well, you're still trying to do the same activities. You're trying to run, jump, contract your quads, move in the world. And so what the brain starts to do is, well, I need a certain level of sensory input to maintain my motor output, to maintain my activities, to contract the muscles, etc. And so it goes, well, my sensory cortex is not getting that information anymore. And so it goes to these cross-modal areas to say, in these areas, these are like the lingual gyrus, precuneus, superior parietal cortex, these sort of areas here. And these areas try to integrate where am I in space proprioceptively with visual information. So in that example, like if you're reaching for your wine glass at dinner, and if you grab it, say I'm talking to you, Julian, and I reach for my glass. I don't look at my glass, but I'm looking at you. I take a drink, I put it back down. I never had to look at my hand or look at the glass. So I could rely on proprioception. I could maintain conversation. I remember where I put it, etc. Now, if I were to hit it or someone moved it or it was slightly off for proprioception, I immediately bring my vision to it and I would create corrections. And so the cross-modal region is what allows you to do that. You had an error in where you thought you were proprioceptively. These cross-modal regions will allow you to use vision or your situational awareness to try to compensate for that. And that's the beginning of what we think happens after these ACL injuries and musculoskeletal injuries, is that you have this lost expected sensory information, causes the brain still trying to keep doing what it did before, so it has to get other information. So it uses this cross-modal integration areas. They come online. Now, you might think that's a fine compensation, but the negative of that is those regions, those cross-modal regions that try to map where am I in space visually with proprioception, they're highly connected to your frontal cortex, because your frontal cortex is what allows you to direct your attention to the various things in the world. And so you want those regions to be highly connected to the frontal cortex, because if there is an error and where you perceive yourself visually or proprioceptively, you want to bring it to your attention immediately, because that means you're at risk for injury or you didn't see something in the world that you felt. So it actually works both ways. There's these really cool studies where they have people see an object and then feel the object while their brain's getting scanned, and the whole cross-modal regions, they all come online when they're feeling it as well. So you could have visual errors, which proprioception is accurate, like optical illusions. There's all sorts of scenarios where you need this information. So the negative for all of this injury, I know these are very long explanations, Julian. Feel free to ask more questions.
No worries.
This. I'm almost done with this explanation now. So the negative for this is you would think this is a sensory neuroplasticity. I'll just use these cross-modal regions to move my leg. That's fine. But because they're highly connected to your frontal cortex, which regulates your attention, this pull causes you to pull attention to control your body. You're supposed to use those resources to interact with the world. So now you've gotten used to using attention and vision to control your body. And then you go back to a football pitch. Suddenly your attention is on anything else but your body. You take a bad step. You don't have the sensory information to correct for it because you got used to using this frontal parietal connectivity, not sensory cerebellar connectivity, and you fail and you essentially have another injury. So let me know if that made sense.
Yeah, thanks a lot. And Dustin, I read on your LinkedIn, you talk about bridge the gap between neuroscience and sports medicine, and how can we do it? Is it like communication, or how can we do it to bridge this gap? And in the future, what is the next challenge to bridge this gap?
Yeah, this is going to be, it's always going to be a challenge. One thing I'm most worried about in this bridging of neuroscience to sports medicine is the number of sort of charlatans or guru kind of people. I'm very nervous about this because I get a lot of requests to review some product, or you do research on some instrument that some company makes, or some like famous physio or whatever wants to use our work to support what he's doing or they're doing or she's doing. And the thing I'm most worried about is the integrity of the science. Because as you could probably appreciate, Julian, this is not, I mean, I've been studying this for 15 years. You know, this is not something that's like really intuitive or immediately grasped, and it can be challenging. It can be difficult to really understand. And I kind of worry that the field of sports medicine will latch on to practices that don't make sense or that aren't effective. So for instance, when we published our first papers almost 10 years ago, I thought it was direct attention on the knee joint that started a lot of this. And I think that's a part of it. But as we collect more data, we now know you don't even have to be using direct visual attention for this cross-modal plasticity. For instance, right now, Julian, I'm looking at you, but you can have a general awareness of like where your feet are and how far you are from the object. So right now, you, for instance, nodded your head, but you didn't bash your head into the wall behind you. But proprioception doesn't tell you where the wall is. And you unless you turn around and see it, or maybe you can see it in the video, I guess maybe it's not the best example, but you have a general idea of how far you are from the wall. So this is a situational awareness, or this awareness of where you are in space that doesn't necessarily hinge on directly looking at it with vision. And so we find that sort of sense is also a part of the compensation as well. And then how you design the cognitive tasks. We've done a lot of work on probably what will be most effective to target the unique neuroplasticity after injury. We could talk a little bit about what that looks like. So what I worry the most with this translation is that people will do things that aren't effective, but they think they're effective. Because sometimes it's a little more nuanced than just doing like, flashing lights and stuff, which those tools can be helpful. But I'm hoping that in the next 5 to 10 years, we'll have enough data to really have the new rehabilitation program of modern era. Because if you look at physical therapy, a lot of the rehab's been the same for 30 years. It looks very similar. And so I really think in the next 10, we're going to see a big change. I hope, anyway.
Yeah. Big challenge for everyone working on it. And I have a question from the audience. And can you recommend us some YouTube channel for virtual reality on our smartphones? Do you have some channel?
So I don't have a channel. That's a good idea. Our lab used to have a YouTube channel where we put all of the scenarios we made in our research papers. I'll try to find that. I'll send it to you so you can use it as a link, Julian. We also have a free app for Android, which has anything we've studied. So we've done papers on moving visual fields like roller coasters for balance training. We've done on top of buildings for landing training. We've done soccer and martial arts kicks for motor immersion during basic exercises. Those are all available in the free Android app. We don't make it for Apple because it costs money to be in the app. For the Apple, it's a whole thing. But a lot of what I do is I just search for first-person view and then whatever I want. Because a lot of what you want to use VR for is to induce a visual error and have proprioception be accurate. And so that's another way to train cross-modal integration is normally it's very hard to induce a visual error. Vision's very accurate. It's very good. Eyes closed doesn't actually target cross-modal processing. It just removes vision. You need an error in vision to target it and get them to use proprioception again. And so any moving visual field, when the person is stable, for instance, proprioception's accurate. You're not moving. Visually, you're moving. It's wrong. It's inaccurate. So that can target the cross-modal pathways. So you could just Google like first-person VR fighter plane or roller coaster or soccer or whatever. And you could use that during balance, during landing, during some of your training. So I'll find the link. If people want to play with the Android app, you just click it, download it, and you can use it. But the YouTube VR is pretty good, just first person, whatever you want.
Perfect, thank you. And I have a few more questions. In Europe, I think in France and in Switzerland, we mostly have 30 minutes for physio sessions. And how can we implement the cognitive load? And do we learn patients to do it themselves at home? Or from start of the rehab and in the end of the rehab? How can we, in 30 minutes, do you mean you work less on neuromuscular and you do to the patient, you will do it to the fitness and you focus on cognitive tasks, or do they do it, how do we manage in 30 minutes?
Yeah, it's a good question. And that's the real crux of this issue is you have very limited time and you have a lot of things you want to do. And so what I normally do is I design the therapy session how I'm going to do it. So ACL patient, I want 5 to 10 minutes on the quadriceps. Maybe I want 5 minutes of range of motion exercises. Maybe I want 5 minutes of coordination, plyometric squats, whatever, and then maybe some flexibility, whatever the patient needs, right? So I go through it and I design it like normal to treat the musculoskeletal impairments. And then I go through is, okay, this quad exercise, this knee extension, I could do that with an external focus of attention. I make them hit a target instead of just doing the exercise. This squat one, I could do it with a dual task. I'd have them look at me and I'll be like, okay, odd numbers are squats, even numbers are lunges. And I have them just do that. So they're staring at me and they execute the movement the whole time. So they don't think about the movement as much. And so I basically go through the exercises and I go, what exercise makes sense where I could add a dual task, where their attention is focused? Can I put their attention in the world with external focus? If I have VR, maybe I can use that for balance or whatever I'm doing. One other thing we use some is the strobe glasses. They're relatively inexpensive. There's a few companies that makes them. If you just Google strobe glasses for sports performance, I'll use those for more functional activities later as they perturbate visual processing. So those can be helpful. So if I'm doing more coordination, those can be good. But really, you can do a lot of this just layered on top of the exercise you're going to do anyway. And so it's not like new exercises. It's more like augmenting what you're already doing. So it shouldn't take much more time. And then for people at home, there's an app called Switched On that I think's free, or it used to be free.
Yeah, it's free.
Okay, they do simple reaction stuff, and I think you can make your own exercises. It's not terrible. It's on a phone. You could at least, the key is you just want to think about how the patient is using attention. And if you can just think about that and go, well, I want their attention off the joint as much as I can, come up with clever ways to do it. If you just start to do that, that's half the battle right there.
Mm-hmm. Perfect. And some people ask, what is the part of what is your clinical part you currently have? And they ask you to come back in Swiss because they have some cheese.
Yeah, I love my time in Switzerland. Were you in Bern for the conference?
Yeah, I was, yeah.
That was it's such a beautiful place. Yeah, I wish I just stayed.
Come back.
Yeah, the food was very good. Yeah, Bern was such a beautiful city. But okay. Oh, so my clinical load. So I used to be 100% a clinician. Then I do a PhD, and I would see patients and over the years it just gets less and less and less as I do more and more science. So now my life is probably 80% in the lab or writing papers, writing grants, doing the science work. I see patients every now and then. So when our sports medicine team to the local area has like a complex patient, sometimes I'll consult and try to help them. But now I just train a lot of the local physios and they implement a lot of this stuff. So my clinical load is mostly limited to just complex cases at this point. And then other people are implementing a lot of this.
Yeah, great. And are you happy enough with that, or would you like to get like more than 24 hours per day to make more clinical?
At this point, I'm really into the science and trying to figure this out because I feel like the problem with science is like everything takes much longer than you think it's going to take. And I get really excited by finding the answer or like I'll be looking at a data set. So I tell my students, my PhD students, I'll be like, you'll be looking at a data set that took you 2 years to collect, and you'll have a question and you'll run the statistical analysis and you'll be the first person on the planet to know the answer to this scientific question. And that's sort of fantastic in a way. And I feel like we talked about before, we're getting really close to really understanding the neuroplasticity of the injury and the sensorimotor coordination error. Just in the last decade since our first papers on this, I kind of wish I could go back and edit them because a lot of my assumptions or conclusions, like for instance, I thought the ACL injury induced most of this neuroplasticity. It would start in the sensory cortex, kind of what I described to you. And it's starting to look like we just finished this longitudinal study where we get people early after the surgery and then we scan their brains as they go on. It looks like it might be driven by the frontal cortex, and our own therapy might be inducing more of this neuroplasticity than the injury itself, which in hindsight makes some sense because your brain will adapt to either your behavior changes or the sensory information it's getting changes. And an ACL injury, you get both. Sensors from H is different, and how you're moving, how you're behaving is different. But our own rehab might be doing more of what we see than I thought, which is interesting in and of itself. So I'm really into the science part now. Now, hopefully, the U.S. government gets its act together and we can continue science. We're a little bit of a problem right now because the NIH has been slowed down quite a bit. But I'm optimistic that we'll come out of this and science will continue. So I'm really involved in that. So, thank you.
You're welcome. I wish it will be better in a few
Me
months.
too.
Dustin, I have 3 last questions. What are your mentors or people who inspired you in your background, in your pathway?
Yeah. So my I had really great mentor when I was a clinician. So he was a physical therapist. He's out in the United States. His name's Terry Grindstaff. He was the first person who I met that was a clinician, but he was also a scientist. So he published papers, he did research, and he taught patients. And then my PhD advisor from over a decade ago now, Dr. James Onati, he let me do neuroscience. So it was a big gamble for him because he had never done neuroscience or brain imaging. And I came in, I had these ideas, and he let me do it. So I'm always in debt to him for like believing in me to do neuroscience. Those were 2 like professional mentors that I really remember. That have been really impactful. There's so many people though over the years. I could probably do a whole podcast on all the people that have made this possible. We don't have to go into them all, but there's just a lot of everything I've told you is probably the work and efforts directly and indirectly of probably 100 people to like get this data, get this literature out there. So I've been very lucky to work with a lot of fantastic people. So it's hard to mention them all. But
and we feel it when we see your presentation. You always start and finish with lots of pictures about people you work with, and it's impressive how many people work to get new data and new science. You know, when you think about it, it's just huge how many people need to work on one topic to get new trends in ACL rehab or whatever. So yeah, thank you for everything, for you and for them and for us. Yeah, exactly. And do you have a book, favorite books in sports performance or rehab?
Yeah, there's a few. So probably for neuroscience, Jeff Hawkins has written 2 books, one called On Intelligence and one called, I think it's called 1,000 Brains. So Jeff Hawkins is a neuroscience theorist, and he writes these books that are easy to pick up and read and understand, that talk a lot about some of the neuroscience I mentioned today. And I think they'll give you insights for therapy and how you think about neural control. They're good books. There's another one I read about a year ago was called The Tale of the Dueling Neurosurgeons. And it features a few French neurosurgeons, neuroscientists actually. Okay. But it's like this history of neuroscience and how up until like 30 or 40 years ago, we had to rely basically on people getting shot in the head and surviving to figure out what that part of the brain did. You know, and so I think people think we're in this amazing time, but it's pretty recent where we've actually had the ability to do stuff. So it's a kind of a comical, interesting look back at history. But the Jeff Hawkins books, I think I give them to all my students, and he's well written and he's very forward thinking. I think those would be interesting if you're interested in this idea and want to have some more science background on it.
Mm-hmm. Perfect. And last question, Dustin, if we need to contact you, how can we do it? Do you have Instagram or whatever?
I don't use a lot of the social media. I'm older, probably. So if people email me, though, I try to always respond. So I try my best. So my email is just grooms, GROOMSD @ohio.edu. But if you look, I work for Ohio University. So if you just Google my name and then Ohio University, you probably find it. I do have a Twitter, but Twitter's, I don't really use it as much. It used to be a lot of academics and scientists have left it, maybe for obvious reasons. It's getting used a lot less. I do have a LinkedIn, which I mostly use just to post when we have positions and recruit students. I'm not on there too much. If you really want a response from me, probably email is probably your best bet.
Dustin, thanks a lot for your time.
Certainly.
And maybe in a few months or in a few years for the new ACL rehab news.
Sounds good, Julian. It was nice to see you again, and good luck.
Cheers.
Cheers.